Hi, everyone. We're going to be doing some chapter 10 problems. So welcome to the session. All right, let's take a look at the first problem. The average barometric pressure at an altitude of 10 kilometers is 210 millimeters of mercury. Express this pressure in atmospheres, bars, and kilopascals. Now, we will not be working with kilopascals nor with bars in this class. We'll just be working with atmospheres and millimeters of mercury. So what you should know about millimeters of mercury and kilopascals, or excuse me, and atmospheres is the following: that one atmosphere exactly is 760 millimeters of mercury exactly. And the origin of this conversion is that if you have a container and you have a tube, and in this container you have mercury, which is a liquid, and you have 1 atmosphere pressure pushing down on that liquid, regardless of the size of the tube, if there is a vacuum in the tube, that is to say there's no air in the tube, the mercury will have a height of 760 millimeters. So hence, 1 atmosphere is 760 millimeters of mercury. Now, in this tube, if it were water, it would be 760 millimeters times 13.5, because the density of water is 13.5 times less dense than mercury. So the column of water would be that much higher. So here's the mercury, and here's the air. So this only works if you have a vacuum in here. So what happens if you don't have a container that's 760 millimeters long, which is 3/4 of a meter long? So what if you don't have one that is that long? So if I extend this and we have a shorter column and it's still pushing down with 1 atmosphere, and this is mercury, well, this whole thing would be filled. So there's only going to be space up here if you have a tall enough of a column. All right, so we have 210 millimeters of mercury. We multiply by 1 atmosphere over 760 millimeters of mercury. Now this is defined, so we have infinity zig figs here and infinity zig figs here. And so here we're going to end up with 2 zig figs because of this, and it's clear to see that the answer is going to be less than 210 because we're dividing by 760. So that looks like about 1/4 or 1/3, right? So let me pull out my calculator and see what we get. 210 divided by 760 is equal to 0.28 atmospheres. There you go. So, of course, this is the kind of work I'd expect to see for a problem like this with the correct number of significant figures. Okay, put the following in order of increasing pressure. Now, again, we're not working with pascals and we're not working with bars. So here, how can I put these in order of increasing pressure? All I have to do is think about it a little bit. So 0.256 atmospheres is 1/4 of 1 atmosphere. And that would be 1/4 of 760 millimeters of mercury. And 1/4 of 760, if I pretend it's 800, would be about 200. So here I know that's about 200 millimeters of mercury. So increasing pressure, I'm going to put 0.256 atmospheres first, and that's going to be less than 363 millimeters of mercury. Another way to think about it is this is almost half of 760, so that's half of an atmosphere. So this is the order. Okay, So that's all you really need here. A sample of CO2 gas has a pressure of 56.5 millimeters of mercury in a 125 milliliter flask. The sample is transferred to a new flask where it has a pressure of 62.3 millimeters of mercury at the same temp. What is the volume of the new flask? So in my class, you do not have to memorize whose law it is you need to use to do this. But here we have our gas in a flask, and we're going to transfer it to a new flask. It's got 56.5 millimeters of mercury in the original flask. In the new flask, the pressure has slightly increased, and because we know PV equals nRT, and therefore pressure is proportional to 1 over volume, pressure is proportional to moles, and pressure is proportional to T. Notice when the P and the V are on the same side, the proportionality is inverse. So here, if I see that the pressure has increased, I know that the volume must have decreased. So I'm going to draw a smaller flask here. And here, the gas is more dense because there's less volume. So here, we have a P1 V1 equals N1 R T1, and here we have a P2 V2 equals N2 R T2. Now notice they say that at the same temperature, so that means T1 equals T2. Now this becomes P1 V1 over N1 T1 is equal to R, and this also becomes P2 V2 over N2 T2 is equal to R. Now if T1 equals T2, they go away. Now, N1 is equal to N2 because the amount of gas here, the moles of gas, so if I draw 10 particles in here, which I'm not going to do, I'm going to put 6 in here. If I have 6 particles of gas here, when I put it in the new container, I have the exact same 6 particles of gas. So that means N1 equals N2, and they cancel out of this formula. So for this problem, we want to use P1 V1 is equal to P2 V2, and therefore V2 is equal to P1 V1 over P2. Now what's really nice about problems like this is even though for R we normally have units of liters, atmospheres, mole K, or liters, millimeters of mercury, mole K, we don't need to worry about that. So the fact that this is not liters does not bother us because our volume will end up being milliliters. So P1 is 56.5 millimeters of mercury. Notice the units are in the problem. V1 is 125 milliliters, and P2 is 62.3 millimeters of mercury. So here it is obvious that our answer will end up being milliliters because the millimeters of mercury cancel. So we have 56.5 times 125 divided by 62.3, and this better come out being a little less than 125, right? Because 56 is less than that. In fact, I'd say that 56.5 is about 10% less than that. So our answer should be 10% smaller than 125. So my guess is about 115 or 112. Okay, and the answer comes out to be not what I calculated. And that's because I used 152, not 125. So let me try again. So here on my calculator, this said 137 milliliters, and I knew it should be around 112, 115. So I knew I did something wrong in my calculator, and I saw that I had punched in 152 instead of 125. So it's good to estimate. And here we get 113 milliliters. So this is the kind of work I would expect to see. You wouldn't really need to show this, but you should show the initial equation that you started with. And I don't expect you to show this. You can do this on a little piece of scratch paper, get the equation that you want, which is right there. P1 V1 equals P2 V2, and then go from there. Okay. Let's put that one off. A 5 milliliter sample of CO2 gas is enclosed in a gas-tight syringe at 22 degrees Celsius. If the syringe is immersed in an ice bath, what is the new gas volume, assuming the pressure is held constant? So we have this 5 milliliter syringe with CO2 in it. And here's my plunger. And we'll make it look like a syringe. So there's a needle coming out of the end here. And here we've got 5.0 milliliters. And this is at 22 degrees Celsius, which is really 273.15 plus 22, or 295 K. Whenever you use these gas problems, it needs to be K for the temperature. It does not work with degrees Celsius. Okay, so here's our CO2. We're going to take this syringe and we're going to put it into into some ice. And so now our syringe is in the ice. And here we have the CO2 and it's 0 degrees Celsius. So the idea here is that the gas is now also 0 degrees Celsius. Here, what is the volume? Assuming that pressure is held constant. So here we have P1 and here we have P2, pressure pushing down on the syringe, and they stay the same. So here we have P1 V1 equals N1 R T1, or P1 V1 over N1 T1 is equal to R. And over here we have P2 V2 over N2 T2. Now, this temperature is 273 K, not 0 degrees Celsius. We want to use 273. So we know that the pressures stay the same, so they just drop out of the equation. We know that the number of molecules of CO2 stay the same, so that drops out of the equation. Because if N1 equals N2, you can just eliminate them. So our equation is going to be V1 over T1 is equal to V2 over T2. Okay, so if you happen to know, that happens to be Charles' law, but we don't need to know it's Charles' law to be able to get it and use it. We're solving for V2. So V2 is equal to V1 T2 over T1. So I do the cross V1 T2. And then since I have V2 T1, I divide by T1 to isolate V2. And now it's just a matter of what I call plug and chug. So V1 is 5.0 milliliters. And here's where a lot of people get into trouble with the problem like this, is they don't realize that that is T2 and they put T1 here. So we need to put T2 here, which is 273. Okay. And T1 is 295 K. Okay. Now really this should be 273.15 and 295.15 rounded to the third, and then rounded to 2 digits because of this. So let's see what we get. 5.0 times, and clearly the answer is going to be about, I would say 4.5, 4.6, because this over this is less than 1. Less than 1 times 5 should be a little less than 5. So 273.15 divided by 295.15. Okay, and I get 4.6 milliliters. So this is the kind of work I'd expect to see for a problem like that. Okay. You have a sample of CO2 in a flask with a volume of 25 milliliters. At 20.5 degrees Celsius, the pressure of the gas is 436.5 millimeters of mercury. So here we have a flask. And it's 25.0 milliliters. And it's 20.5 degrees Celsius plus 273.15, which is equal to 293.65 K. And that's good to the 10th. And we have that the pressure is 436.5 millimeters of mercury. And what else do we have? And we have this many moles of gas. I'm just going to draw 4 dots. We're going to take this and we want to put it in another flask. So to find the volume of another flask B, you move the CO2 to B and find that its pressure is a lot less. So it sounds like a bigger flask if it's a lot less. So we still only have the 4 dots of gas, and here's our cork. So here we've got the V2, which is what we want to know, the volume of flask B. So here's flask A, and here's flask B. Okay. And you find that the pressure is 94.3 millimeters of mercury. And the temperature is 24.5 degrees Celsius plus 273.15, which is equal to 297.65 K. If I did that right. So that looks right. That looks right. Okay. And it is a temperature. I already got the temperature and I got the pressure. And we don't have the moles of gas. We just have N1 and N2. But here, if you take a look, I have 4 dots of gas here. I have 4 dots of gas here. So what is the relationship between N1 and N2? They're equal. So we have an equation that looks like this: P1 over V1, P1 V1 over N2 T2 is equal to P2 V2 over N2 T2. Oops, this should be N1 and T1. So correct that. Now the N's go away because they're the same, and we're solving for V2. So V2 is going to equal, according to this, well, I'm going to do this right here, P1 V1 over N1, over T1 is equal to P2 V2 over T2. We're solving for V2, so V2 is going to equal the cross P1 V1 T2 divided by V2 and T1. So we have to keep good track of what's going on here. So P1 is 436.5 millimeters of mercury. V1 is 25 milliliters. T2, not T1, T2 is 297.65 K. V2 is what we want. Oh, this is supposed to be not, it's supposed to be P2. P2 is 94.3 millimeters of mercury. And T1 is over here, 293.65 K. Okay, so we get V2 is going to be equal to, well, we can kind of figure it out, right? This over this is pretty close to 1, so that should still be about 25. This will go into that 4 times, so 4 times 25 means the answer should be about 100. A little bit more, though, because this goes into that more than 4 times. It's really 4.5. So 4.5 times this makes this, what, 115? So 115-ish is what we should get for the milliliters. And let's see what we get. 436.5 times 25 times 297.65 divided by 94.3 divided by 293.65. And I get 117 milliliters. So I would expect to see all of this work for this answer. Okay. Let's see. Let's see how many more of these I want to do. I think we'll go up through 20 today, or in this session. A sample of gas occupies 135 milliliters at 25.5 degrees Celsius. The pressure is 165 millimeters of mercury. What is the pressure of the gas sample when it is placed in a 252 milliliter flask at temperature of 0 degrees Celsius? Now, we've done quite a few of these so far. So what you might want to do now is pause this recording, see if you can set up the problem, get the solution, and then compare it to what I am about to do. So here I go. You've seen me already drawn little drawings for these things. So I have a sample of gas, and here I'm just going to draw a little cube. and it's 135 milliliters. It's 22.5 degrees Celsius plus 273.15, which is equal to 295.65 K. And the pressure is 165 millimeters of mercury. Okay, now I put it into a 252 milliliter flask, so clearly I have to draw something that's bigger than that. So 252 milliliters, and the temperature is 0.0 degrees Celsius plus 273.15, which is 273.15 K. Now, these are both good to the 10th. All right. Now, the question is, what is the pressure? So P2. So again, we have P1 V1 over N1 T1 is equal to P2 V2 over N2 T2. Now here we have N1, and I'm going to say we have 3 dots. Here we have N2, and when we transfer this gas into here, the presumption is we transfer all of it and nothing else, just the gas. So 3 dots, 3 dots. N1 equals N2. And just to show you how this plays out, we are solving for P2. So here we get P2 is equal to P1 V1 N2 T2. That's the cross. And then I divide by all of the stuff here on this cross except for P2. So I'm going to divide by N1 T1 V2. Okay, I'm going to pause this for just a moment. Okay, that was a brief pause if you noticed it, and I just resumed recording. So I have this over here. Now, you should notice that N1 and N2 are the same amount, so you can see that they cancel. Boom, boom. Now, P2 is what we want, and P1 is definitely going to be part of our equation. So P1, V1 is going to be part of our equation. T2 is going to be part of our equation. T1 will be part of our equation, and I'm going to put that underneath T2 so that they kind of match, and we have V2. So now it's just a matter of plug and chug. So P1 is 165 millimeters of mercury. V1 is 135 milliliters. T2, not 1, T2 is 273.15 K. Now, even though this is good to the 10th, you can see that this has 3 zig figs, this has 3 zig figs, and that's at the moment what is going to define our answer for the number of zig figs. V2 is 252 milliliters, and T1 is 295.65 K. So you can see the K's cancel, the milliliters cancel. So our answer will be millimeters of mercury. And that's why it's important to have the units here, is so that we know what the units are for our answer. Okay, now, when we try to figure out this answer, I think it's pretty clear that 135 goes on to 252 almost 2 times. 2 will go into 165 about 80 times, and 273 over 295 is about 1, a little less than 1, maybe 0.9. So we have 80 times 0.9, which makes this answer about 70 or thereabouts, maybe 75-ish. So let's plug the numbers into our calculator. 165 times 135 times 273.15 divided by 252 divided by 295.65. And so I get 81.66. So 81.7. So I thought this would be around 75. I underestimated what the answer should have been. But this is the kind of work I would expect to see for this answer. And I didn't even expect to see that. I call this Tony's Law. Yeah, it's not Tony's Law, but that's what I call it. Okay, so using Tony's Law is pretty simple. Now, here, how do you know you want to use Tony's Law? You use Tony's Law when there's a change in pressure, change in temp, change in volume, change in moles of gas. That's when you use Tony's law. Okay, so 14 we're going to skip because it says please refer to the book, so that means it was too long to write down here. Let's take a look at this next problem. Ethane, which is C2H6, burns in air to give H2O and CO2. So this is a combustion reaction, which is a specific type of a class of reaction called redox. We know it's redox because we have pure oxygen on one side of the equation, and that makes it a redox. In fact, if it's a pure element on one side of the equation, and that element is not as a pure element on the other side, it's a redox. So what volume of O2 is required for a complete reaction with 5.2 liters of C2? And what volume of H2O vapor is produced? Assume all gases are measured at the same temp and same pressure. So basically, this is in a large room where we're burning the gas. And we start off with C2H6 and O2, and the pressure is 1 atmosphere. Okay, so this is the room before. And here, there is no CO2 and no H2O. We just have these two gases, and the pressure is 1 atmosphere. So here, afterwards, presumably, we don't have any of these gases, and we only have CO2 and H2O gases, and the pressure is 1 atmosphere. Okay, so here's the deal here. When we look at this, we know that PV equals nRT. So that's the ideal gas law. And here we have T1 and T2, and they're equal, correct? Because it says same temp and same pressure. And we know that P1 is equal to P2. So those are the same. So here, if we do a P1V1, N1T1 for any of these gases, here we do a P2V2 equals N2RT2. Now, why don't I put a 2 on the R? Because R is the gas constant. It always stays the same. We haven't had a problem where we've used R yet, but we'll see that eventually. So the deal here is, if we take a look here, we can see that V1 is equal to N1 R T1 over P1. And here we can see that V2 is equal to N2 R T2 over P2. In other words, we could say that V1 is proportional to N1. It's not proportional to P1, T1, and R1 because those are constant. And here V2 is proportional to N2. So in other words, the volume is going to be proportional to the moles. So how does that help us with this reaction? Well, it helps us because of the following. For this, we normally think it's 2 moles reacts with 7 moles to give you 4 moles and 6 moles. But because T is constant and P is constant, they don't change. That means that we can think of these not as being moles, but since volume is proportional to moles in this case, we can think of this as being 7 liters, or excuse me, 2 liters, 7 liters, 4 liters, and 6 liters. And that makes this problem a whole lot easier. So let's see what this problem becomes with that in mind. So what volume in O2 is required for complete reaction with 5.2 liters of C2H6? Well, we would say 5.2 liters of C2H6 times 7 liters of O2 per 2 liters of C2H6, and these are coefficients. And we can do this because this is constant pressure and constant temp. So here you can see the answer is going to be what? Almost 4 times 5.2. So the answer over here should be around 20 or probably just a little bit less. So 5.2 times 7 divided by 2, and we get 18.2 liters. And so here's what I would expect to see for the answer for the first part. What volume of H2O vapor is produced? Same problem, different emphasis. So here we're going to have 6 liters of H2O per 2 liters of C2H6. So it's going to be 3 times this, which is going to be 16 liters of O2, if I'm not mistaken. Yep, I get 15.6, which I round to 2 zig figs, and so I get 16 liters. And so this would be the answer for the second part. So it's kind of convenient that this is at constant pressure because we can think of these as volumes. So how do you know it's volume instead of pressure? Well, if it's constant pressure, it means they're all at the same pressure, which means all the coefficients should be the same. Okay, so however, constant pressure means that these are volumes, not pressures, and that's why the coefficients are different. Alrighty then. So that was a really cool one because it allowed us to see that the coefficients could be thought of as being different. Now, we could do this another way. For instance, we have for this 5.2 liters, we have the same pressure and the same temperature. We could solve for the moles of gas here based on this and this and this. And it gets ugly. So here is what I mean. P1 V1 is equal to N1 R T1, right? So here, when we look at this, if we want the moles of gas, so the moles of C2H6 would be equal to P1 V1 over N1 R T2, T1. This is supposed to be R. Okay, so when we plug these numbers in, we get P1 V1 over R, and here T1. And what was that volume we had? 5.2 liters. So that's the moles of C2H2. So here, if we want to know how many liters of this stuff, first we have to figure out the moles of O2. So the moles of O2 are going to equal P1 P.2 liters over R T1 times, what do we have here? We have 7 moles of O2. So 7 moles of O2 per 2 moles of C2H6. So we have to put this in here to balance that, and it's even going to get uglier after that. Okay. And then finally, to get the, what was the answer? We need the volume. The volume of O2 would then be equal to, basically, volume of O2 would be nRT over P2, or P, yeah, that's it. So we plug this in here, all of this, P 5.2 liters, 1 over RT1 times 7 over 2, and here I'm going to put mole of O2, mole of C2H6, and then here you can see that we multiply, and this is just N, we multiply by R, T2 over P2, and here's the deal. P1 and P2 cancel, T2 and that cancel, R and R cancels, and we end up getting 5.2 times 7 over 2, which is what we did up here so much more easily. So why would you want to do this on the right when you could do this on the left? And the answer is because you're crazy. So we can't do this problem without understanding that these can be volumes in this case, but why would you want to do that? So here, you need to remember this. When P and T are constant, coefficients are moles or liters. When volume and T are constant, coefficients are pressures or moles. That's it. Okay, so this is a good thing to remember. I don't think I've ever done this before in another class because it's just too much work, but there it is. You can see that all works out. All right. I don't know if I'm glad I did that or not. 18. A balloon holds 30 kilograms of helium. What is the volume of the balloon if its pressure is 1.20 atmospheres and the temperature is 22 degrees Celsius? So we have that the mass is 30.0 kilograms. We have that the pressure is 1.20 atmospheres. And we have the temperature is 22 plus 273.15 K, which is 295.15 K. Okay, so what is the change in moles of gas? Because the mass would give us the moles of gas, right? There's no change. What's the change in pressure? There's no change. What is the change in temp? There's no change. So there's no change in pressure, volume, temp, or moles. So what do we do here? We use the ideal gas law. So here, we're supposed to figure out what volume. So the volume is nRT over P, and we don't have the moles of gas. We have the grams of gas. So we need to take this and convert that into moles of gas. So we've got 30.0 kilograms of helium times 1,000 grams of helium per 1 kilogram of helium, and then times 4.01 or something like that. Yep. 4.01 grams of helium per 1 mole of helium. So this is going to give us how many moles of helium. So let's see what we get. You can see that this goes into there about 250 times. 250 times that is going to be like what, 7,500, something like that. Okay, so 30 times 1,000 divided by 4.01, and I get 7,481 moles of helium. Now, this is only good to here because of the 3 significant figures here and here. Okay, so now we can use this formula to figure out the volume. So the volume is going to be 7,481 moles times R, and here the temperature is 295.15 K, and the pressure is 1.20 atmospheres. So what are we going to use for R? Well, R is equal to 0.0821 liters atmospheres per mole per K, or it's equal to 62.4 liters millimeters of mercury per mole per K. Those are the 2 values for R. One R is based on atmospheres, the other R is based on millimeters of mercury. Which R are we going to use here? Well, I'm going to use the one that's more convenient, the one that has atmospheres, because my pressure here is in atmospheres. So I'm going to use R is equal to 0.82, it's actually 0.6 liters atmospheres per mole per K. Okay, so here when I add these up, this is good to here, which is 3 zig figs. This is good to here, which is 3 zig figs. This is good to here, which is 3 zig figs. This is good to here, which is 4 zig figs. So I'm going to be left with 3 zig figs for my answer. Now, when I'm estimating, I usually think of this answer here as being 0.1 or 1/10. So what's 1/10 of 295? 1/10 of 300. 1/10 of 300 is what, 30? Okay. So 30 divided by 1.2 should be around 25 or something like that, maybe a little more. So 25 times this, and I'm going to get a huge number, right? A very large number. And that's just what I have to expect. All right, so let's see what we get. 7,481 times 0.08206 times 295.15 divided by 1.2, and I get a very large number. I get 1.51 times 10 to the 5 and it's going to be liters of helium. So I would expect to see this type of work and this as part of your answer. And I'd even like to see that as part of your answer. Okay, so this is called the ideal gas law. And I'd like to say you use this when there's no change in anything, but you're actually using this for Tony's law. Tony's law is based on this, but it's P1V1. So you have to have two of the ideal gas law to get Tony's law. Okay, so generally you use Tony's law when there's a change, and you use the ideal gas law by itself when there's no change. All right. Okay, there is another equation. I'm trying to remember it. Density is PM over RT. So that's the density of the gas. So that means that, well, actually, we can't do that for this one because we need the volume. And actually, the density of the gas is equal to mass divided by volume. So if we put all of that together, we end up getting volume times P times M. M is molar mass, is equal to MRT. So here we get that the volume is equal to MRT over PM. So here the moles of the gas we calculated to be 7,800, 481 moles. I'm running out of room here. So here we're going to use V is equal to 7481 moles of gas. For R, we're going to use 0.08206 liter atmosphere mole K. The temperature was 295.15 K. The pressure was 1.20 atmospheres. And the molar mass is 4.01 moles or grams per mole. So if we plug all of these numbers in, let's see what we get. And hopefully we get the same volume as this one here. And let me think about this for just a second. It's not going to come out the same because of that. So I must have this formula wrong somehow or other. So we'll skip that and pretend I never did it. Okay, so let's see this. A still cylinder holds 1.50 grams of ethanol. What is the pressure of the ethanol vapor if the cylinder has a volume of 251 centimeters cubed and the temperature is 250? Assume all the ethanol is a vapor at this temperature. So none of this is a liquid, because ethanol is normally a liquid at normal pressure and temperature. This is not a normal temperature. That's very, very hot. Okay, so here we're going to use PV equals nRT. And we want to know what is the pressure. So P is equal to nRT over volume. So let's first figure out the grams. 1.50 grams of ethanol. This is a common abbreviation for ethanol. Now, ethanol has this formula. So 2 carbons is 24.02, 6 hydrogens is 6.06, and 1 oxygen is 16.00. Add those all up together, and you get what? 46. So 46.08 grams of ethanol per 1 mole of ethanol. And let's see how many moles we get. And we get 0.03255 mole of ethanol. And this is good to that 5 because of 3 zig bigs. So now all we need to do is plug the rest of this in here. Now remember, for the temperature, we have 250 degrees Celsius plus 273.15, which is equal to, let's see, 0.15, 3, 7 plus 5 is 2, carry the 1, and we get 523.15 K. And because this is good to the 10, this is good to the 10. So we have 0.03255 mole times R. So here, what is the pressure? It doesn't ask for millimeters of mercury or for atmospheres. I'm going to do the atmosphere one, 0.08206 liter atmosphere, mole K. The temperature is 523.15 K. And then the volume is 251 centimeters cubed. And so we have 251 centimeters cubed times 1 milliliter per 1 centimeter cubed, which is 251 milliliters. Now, that's not going to be good enough because we need liters. So we need to take that and actually do 251 milliliters times 1 liter per 1,000 milliliters, which is 0.251 liters. So I'd want to see that calculation. So 0.251 liters. All right. So remember, I'm circling all the things that I'd want to see in the answer. I wouldn't want to see you calculating the molar mass. You either get that right or you get that wrong, and it affects the rest of your answer. Okay, now we can go ahead and estimate this. Now remember, I like to think of this as being 1/10. So 1/10 of 523 is 52. Now 52 times 0.03, I can't do, but I can do 52 times 3 is 150, which is 100 times bigger than it should be, so that's 1.5. So 1.5 divided by 2.51 is about 6, because that's how many times a quarter will go into a $1.50. So the answer, I think, should be around 6. Okay, so 0.03255 times 0.08206 times 523.15 and divided by 0.251 is equal to 5.6. And let's see, moles cancel, K's cancel, liters cancels, atmospheres. 2 zig figs, because this only gets 2 zig figs. So that's your pressure. So I'd expect to see all of this work here also. Okay, that's enough for this little video. We've gone through numbers 2 through 20, missing just one of them. We'll start off with 22 for the next video. Thank you for watching.